Hi everyone, and welcome back to the Technion's ECE Deep Learning course. I'm Tal, I'm the instructor of this course. And a big part of deep learning and training neural networks is the automatic differentiation engine, or Autodiff in short. And Autodiff makes it possible to efficiently differentiate almost any function. And this is why we can define many loss functions and find the derivatives and update our networks. And in PyTorch, this is called the Autograd engine. And this is the topic this is going to be the topic of this tutorial. And eventually, all we are going to learn today is going to be summed to a single line of code, the loss dot backward, which we saw in the previous tutorials. And we'll see how we build it. And in this tutorial, we're going to learn about the two flavors of Autodiff, the forward and backward. And backward is what is going to be relevant for training neural networks, the backpropagation algorithm. So let's get started. Okay, so here I am. So before we actually dive into the technical stuff, we need to cover some basics from previous math courses. So let's talk about derivatives. So matrix calculus, we will use most of the derivatives as is without derivation. But if you need some spatial derivative or something that you don't know how to take the derivative for, then you can use the matrix cookbook. And you can always go to the right, to the side of the paper and derive everything by hand and just work slowly, and eventually it will work out. So, for example, if you want to, if we're going to talk about a lot of vector multiplication. So if you want to find a derivative with respect to some multiplication. So for example, here is the dot product. So we have xta and atx. So if you want to take the derivative, then we can derive it very slowly and find that the actual term is the actual result is a scalar. And basically you can just calculate the derivative very simply. And of course, when you take the derivative with respect to a vector, then the result will be a vector. So the derivative of the scalar xta is just the vector a. For if you take the derivative with respect to x. Now here we put some common derivatives, and again, if you can't find the derivative you need, then you should take a look at the matrix cookbook. But in this course, I'm pretty sure it's not going to go any farther than these terms here. And yeah, so that's about the derivative part. Now, another name for what we are going to talk about today is called the chain rule. So if you recall, if we have a function f of x, which is a composition, age g of x, then we can find the gradient of f with respect to the input x by using the chain rule. So we have the internal and external derivatives. So we begin with the internal derivative and then the external. So we have the gradient of g with respect to x, and we have the derivative of h with respect to g. Okay. So you've seen this before. It's nothing new. And basically what we are going to do today is we are going to derive backpropagation, and in backpropagation we backpropagate gradients to the start of the networks. Okay, now another core topic is the constraint optimization. We touched upon this just a little bit last time when we talked about regularization. But in the lecture, you have already seen that you can actually derive the backpropagation algorithm by using the constraint optimization outlook, which involves using a Lagrange multiplier. So what is constraint optimization? So basically, we want to find some optimum of a function, minimum or maximum, subject to some condition. So the general case is that we want, for example, to minimize f of x and y subject to some plane gxy equals to 0. So in order to solve this, at least by end, we usually define something called the Lagrangian, and the Lagrangian looks something like this. So we have the original function with some what we call Lagrange multiplier lambda multiplied by gx of y. Now, if our condition does not come in this form of gxy equals 0, for example, if we have x squared plus y squared equals 1, then in order to change it and transform it to this form, then we just move the sides. So basically we will move the -1, so we get the plane g of xy equals x squared plus y squared minus 1, and this is our plane, which equals 0. Now what is the role of this lambda here? So lambda is called the Lagrange multiplier, and the Lagrange multiplier is required to adjust the magnitudes of the gradient vector. So basically the size, the magnitude of lambda is part of the optimization. So what does it look like in illustration? So for example, if you want to maximize f of xy subject to gxy equals 0, then in purple we can see our f plane, and for example this can be our loss function, right? So in purple. And we can also see our condition gxy equals 0, and we can see that in order for us to maximize f and also for gxy to be 0, we need them to intersect. So the intersection point is right here. Now, what are the properties of this intersection point? So at this intersection point, you can see that we have the curves touch each other, right? And when they have a common tangent line, then we've reached our optimum. So basically, what we see here is that, okay, so to explain it, we can talk about the gradient function itself. So the gradient can be thought of as the slope of the tangent line, right? So the gradient of the function, in this case, should be perpendicular to the contour lines. And when does this happen? So the contour lines of f and g are parallel, if and only if the gradients of f and g are parallel. So you can see this is right the point here. So when the gradients are parallel. So this is our, and at this point, what we actually get is this thing, right? And you can see that lambda is required to adjust the magnitude of the gradients. And if we think about, for example, regularization, then in regularization, the users, we set the lambda and we define the magnitude that we want the condition to happen. So, the condition that we want to apply over our optimization problem. And we've seen this before. Now, what happens if we have multiple constraints? So we can have more than one constraint, and actually this is what you've seen in the lecture when you derive the backpropagation algorithm. So basically we will have multiple Lagrange multipliers. We will have a Lagrange multiplier for each term. So the solution, which you can see right here, is what you use to derive the backpropagation algorithm, right? Okay. So that's about it for our let's say recap of our basic concepts. So now let's go talk about the technical stuff and how do we implement all this differentiation in practice in our computers. Okay, so automatic differentiation, or Autodiff in short, and the idea is that we want to compute derivatives of some loss functions, especially in deep learning. And the idea of Autodiff is just compute derivatives of function which are encoded as computer programs. Now, it is a key component in every deep learning framework, and basically each framework, for example, PyTorch, TensorFlow, JAX, they all have their Autodiff engine. And the idea is that we want exact and efficient computation of the derivatives because we are going to have a lot of parameters, and we want to do this as efficiently as possible. And of course, we want the calculation of the derivative to be accurate. So what are the challenges? So it's kind of trivial, I guess. So computing this many derivatives is time consuming. And of course, it can be computationally expensive, especially when we talk about a lot of parameters. So what is Autodiff? And to define Autodiff, we are going first to define what it is not. So it is important because it helps us to frame the Autodiff engine and appreciate what it does behind or under the hood of training neural networks. So we begin with one technique to calculate derivative. So Autodiff is not numerical differentiation. So what is numerical differentiation? So it is a technique that comes from the standard definition of derivative. You've seen this probably at the basic math courses. So basically, to calculate the derivative of x, again, we can take the point x and move just a bit. So this is the age, a very small age step. And we can calculate this term here and take the limit of age goes to 0. So basically, you want age as small as possible. Now, you can clearly approximate the left-hand side by evaluating the right-hand side at a small but non-zero age. And it's very easy to code, right? You can code it in a single line of code, and we will see an example in just a minute. And the cost of this is O of n evaluation of f for gradients in n dimensions. And the problem with numerical differentiation, which is why we don't use it in practice, is that it is prone to error. For example, as you've seen in the lecture, then we have truncation error, precision errors, and errors like this. So let's take a look at a concrete example, so to make things clear. So we have the function, this one, 3x to the third minus 5x squared. Now, we can see that this is a very simple function. You can immediately calculate the derivative of this. So we also defined the exact derivative function. So the derivative is this term here, right? Because we move the 3, create a 9, x is squared minus 5 multiplied by 2. This is 10, and minus 1 in the power. Okay, so we can also code it very simple. So for example, let's take a look at the point x equals 1.5. And we can actually calculate the derivative at this point because we have the exact gradient. Now, the gradient is the slope, right? So if we take a look, if we plot the function here, you can see the value of the gradient at the point x equals 1.5. Now, I'll just mention that there are other ways to estimate this derivative, and this version is called the center difference version, and it's more accurate and prone to less error. So you've seen this in the lecture as well, but for now, let's take a look at the original estimation. Our numerical differentiation. Now, let's take a proper example, right? So what we're going to see now is we're going to pick different values for age, and basically in black, you are going to see our estimation using a numerical differentiation. That means that we are going to take decreasing values of age and hopefully reach the ground truth value, which is marked in red here. This is the one we calculated by hand. Now, as you will see, so let's play this. As you can see, the estimation gets better as we decrease age, but at some point, so you can see the actual value of our estimation, but at some point, we get this, so take a look, and we get this jump because the value is so small and the computer is having a hard time calculating this, and we get some precision error, right? And this makes the estimation numerically unstable. So this is why basically we don't want numerical differentiation because of this error. And when we want eventually we want some neural network to predict some values or generate some images or something like that. And we want this to be as accurate as possible. So we want, when we train the networks, we want the gradient calculation to be as accurate as possible. So Autodiff is not about calculating numerical derivatives, right? Another way to calculate derivatives is called symbolic differentiation. Now, Autodiff is not exactly symbolic differentiation. It does involve symbolic differentiation, but in a minute we will see how we change the symbolic differentiation for it to work efficiently. So the idea of symbolic differentiation is this is the technique that you were taught in calculus, right? So for example, you can define some rules for mathematical primitives. So for example, for summation or multiplication, and you can work by these rules, and you can also code these rules, right? So for example, for summation, you know that the derivative of summation, it's the sum of derivatives, right? And for multiplication, we have this rule here, and you can code this, and there is no problem coding this, but you need to define the primitive. So what we're going to see that in PyTorch, for example, we have this primitive defined. So we have a lot of some primitive functions. So for example, the function that takes the average of numbers, and PyTorch has a rule or as a primitive that knows the derivatives of taking the average, of taking the mean, right? And for example, another function is the ReLU function. So ReLU is also a primitive in PyTorch, and PyTorch, as it already implemented, the derivative of ReLU is already implemented. So basically, this is a rule that is already implemented. But before we talk about PyTorch, let's continue our discussion of symbolic differentiation. So as you can see, this technique is quite mechanical, right? Given that you defined your very complex function with a lot of primitives, and you know the derivatives of all these primitives, then you can define some rules and define the derivative, the final derivative. So there's no reason not to code it, right? So basically, no problem, just implementing a lot of primitives and use it. Now, what is the problem with that? So we have a problem that some functions are not quite mathematical, let's say that, and we don't know how to calculate the derivative of some data structures. So for example, what is the derivative of the following? So if we have a function, okay, not a mathematical one, but a function that we defined in our code, and this function is called draw point x and y, and we want to know the derivative of this function with respect to x. So for example, we are going to have a long chain of functions, and one of these functions is some function that we define by n. So for example, draw point. So now we need to define, in order for the differentiation to work, we need to define the derivative of draw point x and y, and it's not so simple. Okay, so this is one problem of symbolic differentiation, but the second problem, which is I think is more important, is that careless differentiation using symbolic differentiation can easily produce exponentially large symbolic expression, which can take a lot of time to evaluate and can also waste a lot of resources. So here is an example for this. So for example, for the derivative of the multiplication above, this one. So on the right hand side, we have u of x and du dx, which appear separately, right? This u of x and this derivative of u of x. And if you just proceed to symbolically differentiate u, okay, so for example, you take another derivative and plug its derivative into the appropriate place, you will have duplicated any computation that appears in common. Okay, so basically, when you take for the right term derivative again, then you will have du dx again. So you need to calculate it again, but you have already calculated before. So what can you do to spare these calculations and not do them over and over again? So this is the idea of Autodiff. So basically, Autodiff is going to use memory. Basically, we are going to organize symbolic differentiation such that the differentiation is no longer careless. Basically, we are going to use our memory. So we're going to use our activation. We are going to save our activations or our calculations in the memory, or carry them with us as we continue our computing, our calculations. And basically we won't have to differentiate or take the derivative of things that we've already done before. So basically the idea of Autodiff is it is a smart way or an organized way to do symbolic differentiation. Okay, so this is why we said that it's not exactly symbolic differentiation, but it does involve symbolic differentiation. So let's begin. We're talking about the flavors of Autodiff. So Autodiff comes in two flavors. The first one is forward mode, and the second one is reverse mode. So reverse mode is the one we use for backpropagation, right? But first, let's understand what is forward mode. So in principle, exponentially large expression should have lots of duplication, right? Because we are taking the derivatives again and again and again. So it ought to be possible to simplify it to something fast. And basically the idea is to store the derivatives in the memory for some time, so we can use it in the future. So you can think of forward mode Autodiff as a way to organize symbolic differentiation and retain the sharing of intermediate results between the main computation and the derivative. Now, as I've just said, it comes in two flavors, forward and reverse, and the easy one to describe is usually the forward, what we are going to cover in a minute. There is a name for the derivatives here. It's called directional derivatives. And in machine learning, when deep learning, what we actually do is the reverse mode, which is going to help us implement the backpropagation algorithm. And we will cover this later. And it's going to be called, and the derivatives are going to be called direction gradients. So it's just a change of terms, but we'll see what is the difference between the two flavors. Okay, so Autodiff forward mode, it's going to compute directional derivative. So what is that? So we are going to have some fun here because we are going to define a new data structure, which is going to be called dual numbers. And it's very nice because it reminds us of something we've seen in our mathematical past, which is complex numbers. So let's talk about it for a minute. So to do forward mode, Autodiff on a program, you need to do something called the non-standard interpretation of the program. So what we're going to do is we're going to define some data structure that is called a dual number structure. And the idea is that it's going to use something called truncated Taylor series of the form x plus epsilon x star. Now, what does that mean? So basically, maybe let's jump to the board. So we are going to define a new data structure, and dual number is this animal, x. So let's change to green. So x plus epsilon x star. So this is our new number. This is called the dual number. And dual number, you can see that it has the actual value x, and it also carries x tag, the first derivative, so the truncated Taylor series. So it's going to carry the first derivatives with it along the way. So what this dual number structure reminds us of? So we can think about complex numbers. So in complex number, we had the real axis and the complex and the imaginary axis, right? And we defined some animal called I, and we defined I squared to be equal to -1. So this is exactly what we are going to do here. We are going to define the epsilon axis, or the derivative axis, and this is going to be our y-axis, right? The epsilon one. And basically each number is going to have its actual value x, but it's also going to carry the derivatives with it. So just like complex numbers, we now have a way to carry the derivatives with us. Now, why do we need this, right? So let's see how the dual numbers formation helps us calculate the derivative. So when we define arithmetic on dual numbers by epsilon squared equals 0, this is like I squared equals -1 for complex numbers. and by interpreting any null dual number y as y plus epsilon multiplied by 0, it yields our let's call it our algebra, right? So just like complex numbers, when you sum two dual numbers, then you get the real part, right? So the sum of the real part, the x plus y, and the sum of the derivative part, which is x tag plus y tag, right? So for summation, just like complex number. Now what happens for multiplication, right? So maybe let's do it on board. So we have two dual numbers, and we want to calculate the multiplication of two dual numbers, and it's going to look like this. So we open the parentheses, right? Okay, so this is what happens when we open the parentheses, but we defined epsilon squared to be 0, right? So this is our definition, just like we defined I squared to be -1 for complex numbers. So basically what we get here is xy Now you can see something very interesting. Basically, the coefficient of epsilon is the derivative of multiplication, right? So this is what you do when you wanted to take the derivative of x multiplied by y, right? You do x tag y plus y tag x. This is exactly the derivative. So basically, you can see that the epsilon is going to carry the first derivative always. Okay, so this is a nice property of dual numbers. So basically, we carry the first derivative with us, and epsilon is always going to be the coefficient of the first derivative, right? Now we define epsilon squared equals 0, but in theory, we could also carry the second derivative, and then we would define epsilon to the 3 to be the power of 3 to be 0, right? And then our axes would look like they would be 3D axes, right? And we have the first derivative axis and the second derivative axis. So this is just an idea. So the coefficient of epsilon should look familiar. They are just the corresponding symbolic derivative rules, right? So we recovered the rule of the derivative of multiplication. Now, why are we doing this? We are basically setting up a regime where when we apply a function over all dual numbers, then the result is f of x plus epsilon f tag of x tag. So basically, we can always carry our first derivative. So think about a neural network, and you go forward, and you have all these functions applied over your input. And basically, what you do is you carry your first derivative with you. So at each point of the network, you know the derivative because you carried it with you. So you don't need to calculate it from scratch. No, so basically, dual numbers are just a data structure for carrying the derivatives around together with the undifferentiated answer. This is called the primal one. So what we call the real part is going to be called the primal part. Now, this is very nice. And what it gives us, so let's go back to the chain rule. So let's see what happens when we apply the chain rule. So when you have, so here is an example of a very simple composition of functions. So think about the neural networks, and the input to the neural network is a dual number. So basically, the first input is always going to be x plus epsilon multiplied by 0, because the derivatives of the input is 0. The derivative with the input with respect to the input is 0. So how do we apply this composition? So we start from the inside, right? So we have f, and first we open the inner part. So we have g of x plus epsilon g tag of x tag, right? So this is the rules we define. So this is how we are going to carry. So when we first apply g on this dual number of x, then we get the value of x, the value of g applied on the primal part of x, and we also get the derivative of g tag of x. So basically just one step derivatives, right? Because the x tag was already carried with us, so it was already the input to the to g. So basically we only have to take the derivative with the output with respect to the current input. So this is just a one-step derivative. Now when we apply f, so the rules are exactly the same. So we have f, right, at applied on the primal part, what we call the primal part, right? And then we have the derivative part, right? And we only have to do one step derivation. So basically we get the f tag at g of x, right? So this is just the derivative with the of the output of f with respect to the input. And we also carry with us the previous derivatives, which we got for free, right? So this is what we got, and if this looks familiar, then this is just the chain rule. So if you were to take the derivative from the first part, so let's go back to the first part of the tutorial, remember this thing? So just like this, okay? So just like we did here, we got here for free, but we did this in steps, right? We first applied g, then we applied f, and at each step we actually carried our first derivatives, and we actually got that the coefficient of epsilon is always gives us for free the complete or the entire derivation from the beginning. Okay, so if you are if you want to apply a deep neural network, then you always carry your first derivatives, and when you reach the end, when you calculate your loss, you already have the entire history of derivatives, right? So you only need to do the one step. You only need to calculate the one-step derivative of the loss with respect to the input, and you got the entire derivatives for the entire network for free. And of course, we talked about scalars here, like dimension of 1, but this also generalized for higher dimensions. Now, it works for any function that can be composed out of the primitive operations that we extended to dual numbers. So primitives are, for example, summation, multiplication, ReLU, sigmoid, all these functions that we know how to calculate their derivatives, right? And basically, you can define arbitrary programs constructs. So this draw point function, but you only need to define the derivative of this single function, and just basically it will be carried in the entire computation. Okay, so what happens in neural networks? We actually don't work with scalars. We have in general we're going to work with vector inputs, right? So higher dimensions. So in this case, we are going to look at Jacobians, right? Because we need to calculate the derivatives of matrix with respect to some vector. Basically, we will see how we do this efficiently in Autograd, but the idea of forward mode Autodiff remains the same. Basically, we're going to calculate the Jacobian of one step and not the entire calculation, and the entire Jacobian is going to be the multiplication of the entire history. So we just carry the Jacobian with us as we progress in our calculation. Now, the nice thing about this composition is that even though the full Jacobian may be a very huge, ugly matrix, each of the pieces, JFY, is necessarily very sparse. So sparse means that we have a lot of zeros, right? A lot of things that we do not need to calculate, because each primitive FI only operates on a tiny part of the data. Okay, so what we can do is we can look at the result of forward mode Autodiff as an implicit representation of point index family of matrices. And basically, we actually get this nice property that we only need to calculate a one-step Jacobian, so less computation. So what are the advantages and disadvantages of forward mode, and why we don't use it in deep learning? So the advantage is that for any additional output, the additional required number of steps is just 1. Because, for example, if you have this network here and you carried your entire computation and you carried your entire derivatives up to here, up to this edge here, then you now want to add another output, then you add another node, and for example this sinus here, you only need to calculate one more derivative, right? Only the derivative of this step, because you already carried out the entire derivative history with you up to this point. So just one more step and you get the derivative with respect to this output. So basically you can tell the derivative of this output of V6 with respect to the input X1 with just one more computation. So and the disadvantage is, of course, when we look at the input. So if you have an additional input, then basically you need to start the computation from scratch, because you don't have the derivatives of that input. So in deep learning, we usually have a lot of inputs and just one output, which is the loss function, right? So basically this is why we are going to take a look at the reverse mode Autodiff, where the advantage and disadvantage are inverse. Okay, let's move on. So this was for mode Autodiff, very nice. Not used in practice in deep learning, but we have reverse mode for this, and probably you've heard about backpropagation. And let's build it, right? Let's see how it's designed. So when we optimize neural networks, so unlike four modes, we actually care about gradients of the function frn, which is our input, for example, multiple features, and our output, which is the loss function usually, which results in a single scalar, right? And this is why the gradients are usually much more valuable, and they enable multi-dimensional optimization method, multi-parameter, and all this stuff that we do in deep learning. Now, the concept for a gradient of f generalizes trivially to directional gradients. So, for example, when you look at the middle of the network, so in the middle of the network you don't have scalars, you move from a vector to vector. And let's see what is the idea behind it. And there are several nice ideas that help us derive the backpropagation algorithm. Okay, so the directional gradient is a symmetric concept to directional derivative. Instead of going forward, we are going to go backwards, right? So where the directional derivative, the forward mode, is in the direction v. So we have when we took the Jacobian, we carried the Jacobian with us. So we just multiplied jxf and multiplied by v. The directional gradient is the opposite. You start from the end, and then you calculate the derivative. So the idea is to actually utilize memory. So reverse mode introduces both code complexity and runtime cost. So basically, it's much harder to implement reverse mode. We are not going to use dual numbers. And in addition, we are going to use memory. So basically, we are going to manage some storage, and basically we are going to store our activations during what we are going to call the forward path. And in particular, the space requirements of raw reverse mode are proportional to the runtime of f. And this animation pretty much sums it up, what we're going to talk about. So in backpropagation or in Autodiff reverse mode, we are going to have the forward pass. So in the forward pass, we are just doing these multiplications, applying the network, right? And as we perform the forward calculation, just applying the layers, then we are going to save our activation, the resulting values, in memory. So basically, when you have, for example, in the middle of the network, you have a ReLU a ReLU applied over the output of a layer, then the result of this is going to be saved in our memory, right? Now you reach the end, and now you are going to do the derivation calculation step by step, but you are not going to need to recalculate all the values because you've already saved them in memory. So you only need to know the derivatives of the input of a layer of the output over there with respect to its input. And then you just use the values that you saved in your memory. So let's see it. So the idea is that we have this network, for example, and we have the weights. And basically, when we reach the end, we save in memory all the resulting functions here, all the resulting calculations here, and then we only calculate the derivative of the edges. And this is going to be called our computational graph. And each time you perform some operation on your inputs, on your variables, which are going to be called tensors in a couple of minutes, then you actually add an edge to the graph. You add a node and an edge to the graph, to this computational graph. Now it's much easier to understand backward mode, reverse mode in an illustration. So maybe let's move to the board. So we are interested in calculating the function. Okay, just a minute. We are interested in calculation the function d equals a multiplied by a plus b. Okay, and this is very simple. Of course, you can. We're interested in calculating the gradients with respect to a and with respect to b, and it's very easy to do. So basically, we've done this since high school. So it's very easy to calculate dA and dB. So basically dA is just 2a plus b, and with respect to b is just a. Now what happens when you do this in your favorite coding frameworks, so for example in PyTorch? So in PyTorch you define a and b, which are going to be your inputs, and then you start applying functions over them. So for example, the first thing you do is you define your intermediate variable c, and c equals a plus b. So basically what happens here is that a graph is starting to build up, and in this graph we create an edge which connects a and b to this node c, and the mathematical operation that happens on these edges is summation, right? And now you also define the new intermediate variable d equals a multiplied by c, and another edge appears on the graph, and basically it's an edge from a and an edge from c, and the primitive defined here is multiplication. Okay, now we are interested in calculating the gradients with respect to a and with respect to b, and basically what we did here what we talked about is just what we call the forward pass. So basically we calculated these intermediate values, and these are going to be saved in memory. So now we have c in the memory and d in the memory, and we know these values, they are saved, they occupy some space in our storage. So what happens now? So we are now going to do the backward pass, and this is the idea of reverse mode. So in the backward pass, we only need to calculate the derivative of a single edge. So for example, this edge right here, so the derivative is dd to dA, and we know it's c, just a single step derivative. So we have d, which is a multiplied by c, and the derivative with respect to a is just c. Okay. Now for the edge here, so we do the calculation step by step, right? So we have dd to dc, and this is just a. And again, for every edge we do this. So here we have dc db, which is just 1, and here we have dc dA, which is 1 as well. Okay. Now we need to calculate the actual derivative we want, which is the derivative of the output with respect to the input for a network, which are a and b. So here are the rules for the computational graph. The rules for the computational graph is that between edges we sum, and when we traverse over the edges, on the edges we multiply. So let's see the derivative with respect to d. So we just have this part, right? So just c, and now we are going to do the other path. Then it's plus, and now we are going to go on the edges. So we have this one multiplied by this one. So we have a multiplied by 1. So the total is c plus a, and we know we have it in memory. We save the result in memory. So c is in our memory, and c we know that is a plus b. So basically we got 2a plus b, which is just like we calculated here, right? The mechanical one. Now, what about the second part? What about B? Then for B, we have between actually only have one path. So let's mark it with green. So we only have this part. So it's A is just A multiplied by 1, which is exactly what we already calculated, right? So this is the idea. And this is what's going to be implemented in PyTorch. Basically, what you have is a computational graph, and each time you apply some operation, some primitive over your input, then the graph is continue being built, an edge is added to the graph, and you end up with this one. Okay, so here it's everything is right here, right? So we have the intermediate variables, and we can mechanically write down the derivatives of the individual terms, and then we walk our way backwards, right, to compute the derivative over one edge. So we have the derivative of one edge. So we only need to know the derivative of a single function, of a single operation. So for example, you applied value, we only need to know the derivative of value. Similar for sigmoid, similarly for summation, similarly for multiplication, right? Or every other primitive we want. So this expression graph or computational graph, it's very easy to think about and draw by hand, but it's much more complex to implement than the forward mode, right? Now, the nice thing about it is that the backpropagation step always has the same complexity as the original forward propagation step, right? Because here we do not carry our derivatives with us like in forward mode. We only calculate them when we go backwards. So the advantage and disadvantage are opposite to forward mode, right? So for any additional input, the additional required number of steps is just 1. Right, so basically you have the entire graph, and now you have just one input. So you basically need to know the derivative of one edge and one connection in the graph, and basically you're done. And of course, if you add another output, then you need to start from scratch, because you need to calculate and save the entire activations from scratch. Right, so it's opposite to forward mode, but it makes sense. And in deep learning, we usually have this scenario where we have scalar output and a lot of inputs, right? So this image here, this figure here, sums pretty much when to use forward and reverse mode. So basically, when the inputs are much larger than the outputs, use reverse mode, and otherwise use forward, right? So in deep learning, we are in this left figure case, right? So we have a lot of inputs and usually a single output. Okay, so enough of that mechanical stuff. Let's talk about coding, right? So this is the first time we actually should, this is the first time we are going to introduce PyTorch officially. And this is going to be our main coding framework for implementing neural networks. So it's a good opportunity to talk about PyTorch and why we decided to use it in this course. There are other frameworks, TensorFlow and JAX, and also there's MLX by Apple. So there are many frameworks, but PyTorch has gained a lot of popularity, and this is why we're using it. And it's very easy to use, and its the main idea behind PyTorch is to be as similar to NumPy as possible, because everybody that uses Python uses NumPy as well. So at its core, PyTorch provides two main features: an n-dimensional tensor, very similar to NumPy, but can run also on GPUs, right? So this is the advantage here. And the second thing is the Autodiff engine, which is going to be called Autograd, and PyTorch provided it to us, and you've seen it before, and it's going to be a single line of code, loss.backward. We've seen this in the previous tutorials, but what this single line is doing is implementing Autodiff reverse mode, basically, and the backpropagation, and this line computes the entire gradients for the entire computational graph. Now, the word tensor might seem intimidating, but it's just an n-dimensional array or matrix, so basically np.array, what you've seen in NumPy. And a PyTorch tensor is conceptually identical to a NumPy array, right? But we have also other stuff we can do with it. For example, we can put it on the GPU, we can also calculate gradients, and we will see this in a minute. Now, behind the scenes, tensors can keep track of computational graph and gradient, but they are also useful as a generic tool for scientific computing. Now, this illustration here pretty much sums what a tensor is, so don't be intimidated by the name tensor, by the term tensor. It's just a NumPy multi-dimensional NumPy array with additional features. Now, the idea of PyTorch is that most of the function and methods available in NumPy are also available in PyTorch for tensors. So they try to keep the API more like the same. There are differences, but it's very easy to transition from NumPy to tensor. Now, Autograd is the engine or the package that implements Autodiff, reverse mode Autodiff, and this is what we're going to see in a couple of minutes. So why not just use NumPy, right? So basically, you can implement yourself the Autodiff. There are many implementations for Autodiff in NumPy, and NumPy is great, and we are still using it. Of course, there are already extensions for NumPy to work on GPUs. It's called Numba. Check it out if you're interested, if you want to accelerate your NumPy computations. But for model deep networks that use GPUs or often TPUs or other architectures, we can actually get the speedups of more than 50 or greater. So and NumPy is not going to cut it for this thing. So let's see a couple of basics in PyTorch. So for example, if you want to initialize the tensor with the dimensions 5 by 3 and you want to initialize the values from uniform distribution between -1 and 1, you can do that easily. So you also have the shape attribute from NumPy, but you can also call size. So both will result in the same result. And this is just like in NumPy, right? Now, if you want to transition from NumPy to Torch, then the best practice is to call torch.tensor. And in the past, we could also do from NumPy, but it's slower. So just do that. So every time you want to initialize the tensor from NumPy, just do that. Now we also would like to go back to NumPy. So we can just call this function. Or basically, if your tensor sits on the GPU, then first you transition it to the CPU and then call NumPy. Now, why would we want to go back to NumPy? So the answer is very simple. Basically, most of the packages in Python, they support NumPy. So Scikit-learn, Matplotlib, the plotting library. Then when we want to do this kind of plotting or other calculations, we need to move back to NumPy. So it's useful, and we do this a lot, especially when we want to plot stuff or calculate some other stuff like statistics and things like that, right? So it's useful. Now, here is the punchline. Tensors, unlike NumPy arrays, it's a data structure that also has additional fields that help us when we want to build neural networks. So a tensor also has a grad field, and it also has an attribute, a requires grad field. So when you set the requires grad field to true, then every time you apply an operation on this tensor, then a graph will be built behind the scenes. This means that now PyTorch is going to save every result of your operations in the memory and build a computational graph. Now, when you finish your computation, you can call the dot backward and have all the gradients for this graph, right? Now, the gradients are going to be accumulated into the dot grad attribute, which is initially initialized to none. So basically, if you print the tensor dot grad, you can see it will be none, and we will see how we deal with this later when we want when we don't want to accumulate gradients. So remember that we do something called optimizer.zeroGrad, where we zero out the gradient from the previous iteration. Now, to stop a tensor from tracking the history, because when you track the history, it costs us in memory, right? So you can see the memory grows. So we can call .detach, and this will detach the tensor from the computational graph. And every computation that you do on this detach variable or detach tensor will not be tracked in memory. So now, when would we want to detach tensor? So for example, when we want to calculate our validation accuracy. When we calculate the validation, we only care about forwarding things through the network. We don't care about the gradients. So we don't want it to grow our memory in this part. Another way is wrapping your code with torch.grad wrapper, and we will see all of this in practice. But let's see what happens. So let's initialize a tensor with requires grad equals true. So basically the default here is false, but if you want to start tracking operations, you set it to true. Now, when you initialize neural networks, neural networks are wrapping tensors with requires grad equals true. This is going to be called nn.parameter. We'll see this when we progress in the course. But basically, in neural networks, the tensors of the weights of the neural networks are initialized as tensors with requires grad equals true. Now, when we print it, you can see the values of the tensor, and you can also see that the requires grad field is true. Now, you can also print x.grad, and you can see that the x.grad field is none, right? So at this point, we don't have any gradients. So let's perform some operations. So we can add x plus 2, and we can print the resulting intermediate variable. So you can see that y is 333. And we also have the primitive that we talked about. So here we know that the edge of this new edge in the graph is the derivative of the addition operation, right? So we have the PyTorch node that knows how to calculate the derivative of the addition primitive, and it's saved in memory. So you can actually print the derivative function. So if you were to apply another function, so for example sigmoid over x, then you would see here that the gradient function is sigmoid backward. Okay, we can also apply more operations. So we can create the intermediate variable z, and when we print z, you can see that the primitive is the derivative of multiplication. Nice. Now we know that z, so you can see that we also have out. So out is also a variable. So you can think of out, for example, to be the loss function. And you can see that it's a scalar, and the gradient function here is the mean backward, because the operation that was applied here is the mean function. Now let's backpropagate. So now behind the scenes or under the hood, a graph was built, a graph from x to out, from initial variable from x to out. Now in a single line of code, out.backward, we can calculate the gradients over the edges and the gradients of the out variable with respect to all intermediate variables, right? Now out.backward is equivalent to out.backward torch.tensor 1.0, and we will explain in a minute what does this mean, okay? But in the default is that we input nothing, and the default value is just torch.tensor 1. So we can now actually access the x.grad variable, and we can see here that the values. So x.grad, we know that it's going to have the same shape of x, right? So x is this matrix here, and you can see that the value here is 4.5. So this is the output of the out dx. Now what happened here? So we can see the calculation of O, how we calculated O. So O was calculated as the mean of the zi intermediate variable. So if we set zi to its values, then it's this value here. And when we take the derivative of O with respect to x, we can do this by hand, and we get this derivative here, right? Now at the point xi equals 1, which is the values of x, remember, right? Then we actually know that we can calculate it by hand and get the derivative is 4.5, just like the Autograd calculated. So this is exactly what happened here, right? We calculated the derivative over the edges and performed the multiplication. So this is Autograd. This is the very basic idea behind Autograd. Now let's try to dive a bit deeper to what Autograd did here. Now, if you remember, then we care about gradients, right? And basically when you look, for example, at the middle of the network, you have a vector input and a vector output. So basically it's not a gradient, right? It's a Jacobian. So what we see here is that if you have a vector valued function, y equals f of x, the gradient of y with respect to x is what we call the Jacobian matrix, right? It looks something like this. Now, Generally speaking, Torch Autograd is an engine for computing vector Jacobian product. So if you recall in the first or the second tutorial, I told you that these frameworks, PyTorch, TensorFlow, JAX, they all have a trick to calculate the gradients, which does not require us calculating the entire Jacobian matrix. And this is the nice property of these engines, right? So basically the Autograd engine computes vector Jacobian product. Let me stress this next part. Autograd does not calculate Jacobians. Autograd cannot calculate a Jacobian matrix. It can only calculate the vector Jacobian product. Now this is a trick, right? We can only get the resulting gradient, which is a vector Jacobian product. Now, if you remember from the basic machine learning course, you had something, you probably learned about something called the kernel trick. So the idea is very much the same. How can we get the multiplication of two feature vectors, but without calculating each cell separately? So the kernel trick did this for us. And here, to calculate the gradients, we are not going to compute the entire Jacobian. We are going to use Autograd, which is an engine for computing vector Jacobian product. So let's see what this means. So given any vector v, we can compute the product vtj. Okay. Now the idea is that we don't need to calculate j. Okay. So we can just calculate this product without calculating j, which can be very expensive to calculate, right? Now, the reason we can do this is because we assume that the output of a neural network, the output of the loss function, is always a scalar. So this is why we can do this trick, right? If the loss function was not a scalar or had multiple outputs, we could not do this trick, and basically perhaps we would have used maybe an Autodiff forward mode. Now, let's see. So if v happens to be the gradient of a scalar function L, the loss function, right? Then we can then v, okay? Then v actually equals the resulting gradient of L with respect to y, right? So this is what happens here. We have the Jacobian matrix, and we have this gradient of y. And basically what we calculate is this product here, and we get the resulting gradient of L with respect to x, but without calculating the entire Jacobian matrix. Okay, so this is the trick, and let's see how it works in practice. So if you recall, when we call backward, so it defaults to backward torch.tensor 1.0. Now the reason this is default is because we assume that we start from scalars. And this is why the input here, this v, what we call the v down there, is the scalar. So basically, this is what we did there. Now let's see, for example, here. So x is now initialized as a vector of size with dimension of 3, and now we apply some operations, a lot of operations, and we can see that y is also a vector, right, of the same dimension. So if you want to calculate the gradient of y with respect to x, it's no longer called the gradient, it's called Jacobian, because the output is a vector and the input is a vector. And Autograd cannot compute this. So basically, if you were to call backward without any input over y, it will throw an error that tells you that it cannot calculate the Jacobian. So what it can do is, if you give it an input vector, so for example v here, right? So we initialize some vector v, and we now input to the backward function v, then we calculate the product jtv, right? So, and this is possible, and this is absolutely possible. And now you can get the gradient with respect to x. Now, what can we imagine this thing that happened here? So you can think of, for example, so let's go to the board maybe. So we have this example here, x and y. So x is of dimension 3 and y is of dimension 3. So this is like the middle of a neural network, right? Now you can calculate the Jacobian of y, of jx, of the derivatives of y with respect to x. You can do that with Autograd. What you can do is for example, say that you can, for example, say that there is from some point in the network there is a loss function, and you calculate the loss function with respect to y. So you can imagine another part of the graph here, right? That calculated the gradients for the other half of the graph, and now the only thing you do is you give this v to PyTorch and you calculate v transpose j of x, and then you get the derivative of L with respect to x. So this is what you can do with Autograd. You can't calculate the Jacobian. So this is the Autograd engine. And now let's see just a couple of more examples. So basically, if you want to perform some operations on your tensors but without tracking gradients, then you can wrap your code with torch.nograd. And basically, this is useful, for example, when you calculate the validation accuracy and you want to forward through your network many inputs, but you don't want to calculate the gradients of the inputs. So basically, you just you can do this computation more like faster without calculating gradients. Another thing you can do is just detach. So basically, this usually do the same stuff, but maybe you just want to detach not the entire network, just some parts of it. So basically both are useful. So this animation here, which is what we are going to end up here, is what happens in PyTorch when you define several variables, right? So on the fly, a graph is built in the background, right? And the graph is built using your inputs and the primitive defined in PyTorch. So for example, matrix multiplication, addition, and tangents and hyperbolic tangent, right? They are all defined in PyTorch, and we know the gradients. So basically, when we start from a scalar, we can just call dot backward without any input. So we just can calculate the derivative over these edges very efficiently. Now, in PyTorch, we can also draw the computational graph. So we saw the TorchViz package. So basically, we can give it your model, and it will draw your computational graph, and you can see all the primitives here. So for example, multiplication and addition and sigmoid, and all of this can be actually be printed out. So it's nice. And that's about it for this tutorial. Thank you for watching. There are more videos here if you want to dive deeper. And thank you.